The F block series is more like the sign over the entrance to hell in Dante's Inferno. All hope abandon ye who enter here. Alright? Because it gets really goofy, and you actually see that reactivity-wise, the entire row of lanthanides are more similar to each other than the columns are. And so we don't even want to deal with that. That's something that you deal with in a senior level chemistry course because you don't have anything else better to do. We can analyze our bonding simply by dealing with the S and P orbitals. Those are the ones that are going to be the most important, and they'll establish our three primary types. Let's go back and add a piece of notation. Lewis dot structures. Very abbreviated way to establish what the valence shell is. We take the chemical symbol for the element, and in this case, oxygen. How many valence electrons will oxygen have? Okay, it's not 8, it's 6, right? Because 2 of the 8 are in the first atomic orbital. So you gotta be careful. When Lewis dot structures are valence electrons only. The first 2 went in the 2s orbital, and then you have 4 more. 1, 2, 3. And it doesn't really matter, but that's just my way of keeping up with S, PX, PY, PZ, whatever. Lewis dot structures are very valuable in being able to identify what's going to occur here. Okay? Because we can see the valence electrons directly, and we can bond them directly. Let's make a molecule. Let's make an ionic bond. Let's take lithium fluoride. Alright. Now, lithium has how many electrons in the valence shell? 1. Alright. And so there's our Lewis dot structure for lithium. Fluorine, how many electrons does it have in its valence shell? 7. All right. All right. This is where determining why things line up stoichiometrically. Why water is H2O and not HO. Why lithium fluoride is going to be LiF 1 and 1 and not LiF2 or LiF3 or Li2F or something like that. All right. Lithium, we know, alkali metal, very energetically favorable to be able to release that electron. Fluorine, energetically beneficial to accept the electron. Right. So what do we see happen? Turning this into now positive lithium ion, negative fluorine or a fluoride ion, and that gives us now the compound lithium fluoride. If you do that as an orbital diagram, really quickly, worth running through, here's lithium, right? Here's fluorine. For purposes of showing bonding, I'm going to write it in reverse. There's lithium, there's fluorine, correct? As I wrote fluorine is the mirror image to be able to show the bonding. So lithium comes in. It does cost energetically. We gotta pay lithium for that electron. But what fluorine's willing to pay exceeds what lithium wants. And so we see that there's a net giving off of heat, and we see now, is fluorine happy?
Yep.
By lithium. It's only got two, but that's the that's the first atomic orbital, it only needs two. All right, we're good there, everything's good, we've made a compound. Whether you do it from Lewis dot structures, or whether you do it from this way, what you see is that bonding is all about creating that stable valence shape. Now, it doesn't matter, all right? We do have to be careful with ionic bonds, all right? Because when we start calculating, when we start talking about formula weight versus molecular weight and things like that, ionic bonds occur when you have two atoms bonded together and their differences in their electronegativities are 1.7 or larger. So you take the electronegativity of one, of the larger one, you subtract the electronegativity of the smaller one from it. Let's see, did I have that electronegativity chart?
We'll be given the chart.
Oh, yeah. I'm not even expecting to memorize that. Okay, so fluorine has an electronegativity of, I think that's 3.98. 3.98. Lithium has an electronegativity of 0.98, so I'm going to subtract the smaller one from the bigger one, leaving me with a net electronegativity difference of 3. Is that bigger or smaller than 1.7? Bigger ionic bond, which gives us some very interesting characteristics, right? Ionic molecules don't exist as individual pieces, all right? Because when you move them in the solid phase, ionic molecules form a lattice structure like you see on the bottom right-hand corner. You get crystals, right? Salt crystals, basically, right? Isolating a single molecule of lithium fluoride, impossible, right? Because, and the reason is because you have such a charge difference that crystal lattice gives you a way to stabilize that charge. You can, because each positive charge is basically surrounded by 6 negatives, and each negative is surrounded by 6 positives. And so you've got a way to balance out those extreme charge differences in the formation of that crystal lattice. So as we'll see, when we make reference to the molecular weight of an ionic compound, we're actually referring to the theoretical formula weight if we could isolate one of them. We'll talk about that tomorrow. But once we move them out of the solid phase, right, you do not find lithium fluoride molecules floating around in water. What you find is that when they're dissolved in polar solvents like water, it actually becomes more energetically favorable for them to dissociate from one another and live life as this and this independently. And so what you'll do, you'll find these floating around. You'll find these floating around. If you try to pull the water out, what you find is that as you dehydrate this thing, these things start getting closer and closer together until all of a sudden it's more beneficial for them to become that crystal lattice. And they crystallize. And that's when when you take all the water out of, when you start boiling off salt water, and all of a sudden you start seeing salt crystals on the bottom of the pot, that's what's happening. It has a lot to do with entropy. A lot. All right, but we'll deal with that when we get into thermo. But, oh, this is a situation of complete and total electron donation, right? Once this thing, once you donate the electron, that electron belongs to fluorine, right? It can get it back if necessary, but you gotta go through a lot of work to do it, all right? Any of you ladies, if you got an engagement ring, I'm done. All right, any of you guys ever given one? Oh, good God, please, okay, thank you, somebody agree with me, I'm not the only one here. All right, you ever tried to get one back?
No, unfortunately,
Okay.
I'm still stuck with this.
I feel you, brother, I feel you. All right, we're kidding. Anyway, if you've ever tried to get one back, it's not the easiest thing in the world to do. You can get it back. All right, sometimes it's just easier to just let them keep it, but you can get it back without major physical injury to yourself. Most of the time. Anyway, you can get out of it without a court battle, let's put it that way. Covalent bonding is kind of after marriage, we'll talk about that in a minute. But ionic bonding is kind of the engagement period. The donation of the electron or electrons is the engagement ring. Here you go, this is yours. We're going to be paired up, but we can still kind of go and do our own thing in the right set of circumstances, right? You can still hang out with your buddies while they're planning a wedding with their friends, whatever. I realize this being stereotypical, but whatever. Anyway. But the electron still, all right, the engagement ring, you don't keep it with you, all right, right? She keeps it with her. All right, wherever she goes is where it goes. Even though you gave it to her and now y'all are connected. That's the general idea of an ionic bond. It is complete and total electron donation, right? And when you don't see these two in isolation, just one unit, one of each. You see a crystal lattice in solid, or you see an ionized structure in the gas phase and in the liquid phase. All right, but isolating one and pulling it out of solution is practically impossible. That's when they are molten or when they are in the aqueous phase, and here's some terminology, and this is important, all right? Aqueous phase is not the same thing as the liquid phase of a pure substance, right? Water is a pure substance, right? It has a liquid phase, a solid phase, and a gas phase. Something being in aqueous phase means it's dissolved in water, is the strict definition of it. So when you're reading material and it says this is a liquid or this is in aqueous phase, those are two different things. They are very good conductors both in the liquid and in the aqueous phase, in particular in the aqueous phase. This is the very reason right here. Unless the water has some type of ion dissolved in it, it is not a good conductor of electricity. Right? Once we did away with metal pipes, the idea, anybody ever been told by your grandmother, right? Come in a lightning storm, get out of the shower. Mm-hmm. That's because they grew up with metal pipes. And metal pipes put ions into the water. Lightning strikes the house. The metal pipes, that don't ask me why, metal pipe typically served as a nice ground connector between the ground rod and the inside electrical box. Real smart. Don't know why they thought to do that. Stupid. Anyway, but you've now got metal pipes which are dissolving ions into the water. The water, you got a metal drain, you got a clear connection right there. Now we got PVC. PVC does not connect or PEX. PVC does not conduct electricity like metal does, right? And if you completely deionize the water, you're not going to conduct the magnitude of an electrical current that you would if you have high amounts of salt dissolved in the water, okay? Now, this is one of those situations where we start bringing in this idea. Oxidation state, electronegativity, all that's probably good for chemistry one, but oxidation state does overemphasize the effect of electronegativity. Right? It establishes it as an absolute. Right? In reality, in the solid phase, there is still a little bit of sharing going on, but not to any appreciable degree, not to any impact that is going to impact the chemistry that you're concerned with. But it is nonetheless there. Those are ionic bonds. Now, those are by far not the most common type because they only occur between atoms of extreme difference in electronegativity. Atoms that can basically grab an electron, hang on to it, and say, no, you can't have this back. By far and large, the most common type of bond is a covalent bond, of which we have two different types. Now, unless you're dealing with two identical atoms that are bonded together, you're going to have some degree of electronegativity difference, meaning that the bond is going to have some polar character. Right? An ionic bond is almost an absolutely polar bond, but a covalent bond has varying degrees, depending on the difference in the electronegativity. The reason this is because the energy required to completely transfer the electron from one to the other is a little bit more than you get out of the fact that it doesn't. In other words, we're not willing to pay as much for this electron. And they want more for it, call it electronic inflation. Right? Not worth as much, but they want more for it. And so it really doesn't energetically benefit them to go through the process of fully excising that electron and donating. However, there's a middle ground. They can share the electrons. Right? And it's literally a situation of, it's used figuratively, but it's a very good analogy. This is the post-wedding day bond here, all right? They each get to claim the electron for themselves, right? So, married, legally, you both own the house, right? And when you're out with your buddies, you say, when you go to leave for the night, you say, I'm going home. I'm going to my house, right? What you say? I'm going to my house. Because if you feel like I'm going to our house, you gotta go talk to somebody. Because there's obviously people around that nobody else can see. You say, I'm going to my house. Or depending on what the context is, I'm going to my house. When she's, at your mother-in-law's or whatever, or out with her friends or whatever the case, if she goes to go home, what does she say? I'm going to my house. Now, on paper, you both own the house. You both are responsible for the note. You both, in court, you're both own the house, all right? You file bankruptcy on it, you both take the hit on your credit, not just one of you. In the context of covalent bonding, that's the idea. They both get to claim the electron to their own mutual benefit, but neither one of them really owns the thing anymore. It's more of a shared asset. Right? Generally, non-metallic elements are involved, and if you want pure covalent bonds, it almost always will be non-metallic elements. Right? But it really comes down to the difference in electronegativity. Between 0 and 0.4, we classify those as purely covalent. They don't have enough polar character to them to actually do any type of intermolecular bonding or intermolecular forces. Between 0.4 and about 1.7 to 2, depending on which book you read, that's what we classify as polar covalent.
What number do you want us to go with? Because right here it has kind of two.
Yeah,
You want us to stick with the 1.7?
go with 1.7. 1.7 is what I learned, therefore that's what I'm gonna teach you. Again, it's all depending on what book you read, all right? And who wrote the book. I'm not gonna quibble, as long as you can. If you wrote me out 3 sentences that said, you know, look, this is right on the margin, it's gonna have some polar character, and it's gonna have some non-polar character, and depending on which atoms are involved, it's gonna dictate which part's more important, full credit. That's, you know what you're talking about, right? I'm less about the exact number and more about, do you understand why it is that right in there, we have a cutoff. You gotta pick a cutoff at some point, you know, and just deal with a certain number of exceptions. Let's look, though, at a true purely covalent bond. That's a good place to start. We have 7 molecules that form, and these are the 7 diatomic molecules. And that seems to be a staple of chemistry 1. Memorize the diatomic molecules, don't do anything else. All right, so they are what? Hydrogen, nitrogen, oxygen,
chlorine,
bromine, and iodine, for those of you who are reading them off the notes. I guess I should have thought about that before I asked, but hey, use the resources. All right, yeah, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All right, all of the halogens, basically. It's assumed that astatine would be the same way because it's in the halogen column, but again, we can't get enough of it to really know. But let's look at this. Let's use the hydrogen out, all right? So I have a hydrogen here with its 1s shell, and I have a hydrogen here with its 1s shell. How many electrons does each one have? One. Right. Now, nobody else is around. This is a container of pure hydrogen gas. Now, these things are very, very reactive, right? It is to their benefit energetically to pair up. Well, if nobody else is around to play with, so we'll play with each other. So we get together and we form a hydrogen molecule. And let's talk about why this is. Hydrogen is a good example of this. Right? This is your first thing. There's a very limited amount we're going to do with molecular orbitals, but this is how it works. Right? Here's the atomic orbital for each hydrogen. Molecular orbitals, though, what will happen is these things will overlap with each other, and it creates the same number of molecular orbitals as you did atomic orbitals. But it creates a bonding orbital represented by sigma, and then an anti-bonding orbital represented by sigma star. And we fill from the bottom up. Okay, again, 2 per orbital. Vertically, this is energy. That first bonding molecular orbital is of a much lower energy than either of the 2 atomic orbitals. And so energetically, these things can stabilize by forming a hydrogen molecule. Right? Now, we write that, again, that's about the limit. We're going to look at water, but again, this is about the limit of molecular orbitals that we're going to do. But we write that quite simply as, all right, these are in the same orbital between these 2 atomic centers. We write that as a single sigma bond. Right? Sigma bonds are on the linear axis of the molecule. They allow free rotation around each other. In other words, those atomic centers can spin, do whatever they want to, right? But they are bonded together by virtue of this. Now, and this is far more energetically stable than either of the two individually. This is why, in order to break this bond, I've got to put some energy into it. In order to make, it takes energy to raise an electron to a higher energy level. I've got to put energy into it to break those apart, to put them in those two higher energy levels and separate that molecule. That's why bonds require energy to break. Now, so that forms a single covalent bond. From an electronegativity standpoint, I erased that a little bit too quick. Would there be any reason for one electron to spend more of its time over here than over here? No, they're symmetrical, it's indistinguishable. They got equal pulls, all right, on each other. Let's look at another one. Let's consider, hydrogen chloride has a single sigma bond in the middle of it. Now, hydrogen has the 1s electron, right? Chlorine, we're going to do just the valence shell, which will be, so it's the neon configuration, and that is 3s, 3p, that, right there. What's the emphasis for these two things to bond? This is chlorine. This electron can go where? Right there, and then you get that single sigma bond right there between the hydrogen and the chlorine. Now, the question is, what character does this bond have? Is it covalent, polar covalent, or ionic? The only way to know that for sure is to go look up the electronegativities for these things and do the math. Now, chlorine is, I can read that, 3.16, I believe. Hydrogen is what?